Hello, everybody. Welcome to Listening to the Wind, the IWSA weekly interview series. And I'm delighted today to be able to sit down with Simon Schofield, the CTO of BAR Technologies. Hello there, Simon. Thanks for joining us.
Hi, Gavin.
And I'll just give just a quick profile, not to big you up too much, but give our listeners or viewers an opportunity to know a little bit more about you. So Simon is, as I mentioned, CTO of BAR Technologies, with over 20 years at the forefront of Grand Prix racing yacht development, including multiple America's Cup campaigns, Volvo Ocean races, and many others. He's the head of he was the head of design at BAR Land Rover, the British America's Cup entrant in 2016, until he left that to set up BAR Technologies, co-founding that along with Martin Whitmarsh. So welcome to Listening to the Wind, Simon. And I'm going to hand this straight over to you for what I think is going to be an extremely interesting presentation. So please take it away.
Thank you, Gavin, and thank you for everyone that's joined us to watch and listen. And as Gavin mentioned, I'm the CTO of BAR Technologies, and we formed the company in 2016, 2017, actually off the back of the British America's Cup team. And the fundamental philosophy was to take some of those learnings, the techniques, the design techniques, design tools, DNA and general philosophy that we apply in the high-end engineering world of the America's Cup, and apply it to the wider marine industry. We're a maritime innovation company, and we focus very much on simulation-driven design and using our tool sets to develop using very modern techniques what we hope is the latest and greatest tools and products. So today, obviously, we're here to talk about WindWings, which is our offering to the wind technology for ships industry. And I'm going to take you through a little bit of our development process, where we're at, and where we hope to go in the short future. So just a little bit more about us to start with. We're a medium-sized engineering consultancy firm, and compared to a traditional naval architecture firm, we're very multidisciplined. So we cover a wide range of skill sets in-house, and that allows us to provide a very rounded turnkey solution. So some of our skill sets are kind of traditional naval architecture, normal stability, safety, hull development, all the things that you'd expect a normal naval architecture firm to do, but also a twist on that where we're using neural networks, advanced AI techniques to up the game when it comes to optimization techniques. And that's applied not only to hulls, but across the whole range of products that we deliver. Then we've got aero and hydrodynamicists in-house. We have kind of a world-leading CFD capability, and a lifetime of originally tank testing and validation has brought that up into the kind of the modern era, where it's now our go-to tool. And interestingly, in the America's Cup, the use of tank testing or wind tunnel testing has now been banned for a number of years. So everything has to be done in that digital simulation world. And then combining all of our simulations together, and probably at the key and the cornerstone of this product and this project is our simulation and performance analysis tools. And we're basing that around a bespoke, up to 60 degree of freedom maritime prediction software, which has been developed fully in-house, and we'll come on to talk a lot about that during this presentation. And then finally, two other areas that help us kind of deliver our ideas are mechatronics and control engineering team that borrows heavily from the motorsport arena, and we lean on the latest techniques to develop bespoke control systems, telemetry, data analysis, to ensure that we are extracting the maximum performance out of any product we design, and we understand the real life performance versus simulated performance. And then finally, a full team of in-house design engineers, which allow us to undertake everything through mechanical design, advanced structural design of both steel and alloy and composite structures, but mechanical, electrical, weight estimation, and turning our products and ideas into reality. As a business, we are entirely focused on sustainability, with the majority of our projects looking at reducing greenhouse gas emissions and CO2, so WindWings being one example. And we're also heavily involved in the crew transfer industry for CTVs in the wind turbine industry, where we have developed a new product range which is reducing emissions by up to 30% and decreasing vertical accelerations by 70%, and obviously increasing crew comfort. But obviously, kind of the shipping industry has this big challenge ahead of it, and the reduction of CO2 in line with the IMO's requirements. And we want to play our part in delivering solutions to help that. And I don't think there will be a golden bullet to solving the problem, and it's going to be a case of combining lots of technologies to give not only a solution which reduces the greenhouse gas emissions, but also reduces them in an economically viable way. So I talked earlier on at the start of the presentation a little bit about our 6th degree of freedom VPP, which isn't a variable pitch propeller, which often I get corrected on in the shipping industry, but it's the velocity prediction program. And ultimately, the version we've developed specifically for ships, not just for wind technology on ships, but ships as a whole, is developed as a performance digital twin, which also optimizes live and accurately simulates the interaction between multiple complex elements on a ship. So hulls, propellers, rudders, wind in this case, the effect that has on engine loading. And it allows us to simulate and holistically model the performance of a ship, and then we integrate that into an in-house weather routing routine, which has been specifically developed for wind-assisted ships, and allow us to give statistical analysis on the savings that we can make on a Pacific route for a Pacific client on a Pacific ship. And this tool was developed before we even got into the development of wind technology directly. And before we could start developing a wing, it was important that we understood what the wing had to be able to do. What was its performance profile? How did it look in terms of a physical body, as in what did we want it to do, not what did we want it to look like. And to do that, we turned this tool on its head, and we analysed many routes and said, asked the optimizer the question of what would the wing look like to maximize the fuel saving? What does it lift to drag curves look like? How do we maximize the use of it? How do we ensure we've got good yaw balance on the vessel? That rudder angle, for example, doesn't become a limiting factor. How do we balance the vessel? And we asked all these difficult questions of ship seat, which you really do need a tool like that to answer them. And then we use that to guide us in the direction for the development of our wind technology. And what we ended up with is a multi-element wing, and we'll see an example of it in a minute. But I always use the aircraft analogy when I'm explaining why we've ended up where we've ended up. And a single element wing, or even a single element with a small flap at the back, which is what you see in a traditional aeroplane when it's up at cruise altitude, is very efficient in terms of its lift to drag ratio. So it creates a lot of lift for a minimal amount of drag, and in that terms it's very, very efficient. And that's what you see when a plane is cruising at altitude, because it wants to be able to fly and burn as little fuel as possible. So for a given amount of lift, it wants to minimize its drag. But it means there's a limit to the amount of lift and the amount of power it can be produced. And that's the same as what we traditionally see when we develop a wing for the America's Cup boat. We're trying to develop a very efficient high lift to drag device. But what we see when we use ship seat to analyze the requirements for a wind-assisted propulsion device on a ship, is that actually the aerodynamic drag associated with producing the lift is very small compared to the global drag of the ship. So what we're actually looking for is power and grunt. And we want to produce as much lift as possible for a given area. And we don't mind if we pay a little bit more drag for that, because in the grand scheme of things, that drag is still very, very small. And to achieve that, we end up with a multi-element wing, which is very similar to that you'd see on an aeroplane. And what a plane is doing when it's transformed into a 3-element wing when it's coming into land, or even a 4-element wing, is that it wants to fly slower, so it wants to produce as much lift as it possibly can for a given speed, and it doesn't worry so much about a little bit of drag, because it's only doing that at the point it's coming into land. And that's exactly the same philosophy we've taken. We're maximizing the amount of power and hence thrust that we can produce from the wing at the expense of a little bit of drag. But when you look at the ship holistically, it represents a significant net gain. So this is our technology, and these are some examples of, it's actually slightly out of date compared to the latest iterations, but this captures the concept. It's a 3-element wing, which we can invert the camber on, so we can produce a highly cambered shape on both port and starboard tack, and we can produce an awful lot of lift. Safety is obviously really important. So we have two ways of depowering the wing when the wind conditions become too high. One is we can feather it, and it's configured in such a way that in the case of a total power failure and the wing is up, the wing will feather to a 0 lift minimum drag configuration, and we spent a lot of time modeling the effects it has on turning circles and minimum powering requirements of the ship to ensure that we are not endangering the ship, and we're not. The alternative is we can also fold it down flat, and obviously that has additional benefits when you come to look at port operations or getting under bridges and other instances when maybe you don't want the wings erected. We're heavily involved with class, flag, and various companies looking at mitigations for visibility, so working on bridge designs, the use of cameras, the use of additional radar, augmented reality. So we're trying to bring a rounded solution to the party. And when we're doing all these simulations and we're looking at our savings, going back to ship seat, we're always looking at simulating reality. So we're not cherry picking. We're not saying in these perfect conditions we can save this much fuel. We're always looking at the negatives, so the effect of the rudder angle to maintain a straight course and balance the effects of the additional drag from leeway, the effects it has on propeller efficiency curves, the effect of engine efficiency due to the fact it's not necessarily operating at its most optimum setting. And we're then routing that and providing routing data based on kind of 10, 15 years of historic weather data. And on a typical global route, we're seeing savings on a retrofit of the high 20s, and then on a new build in excess of 30%. And that's based on an MR2 with 3 wings fitted. There we go. And to give that some context, we believe the equivalent for 4 rotors is about 14 to 15%, and that kind of plays out with what we're seeing with the published data from some of the testing that's been published. So this is full steam ahead for us, and I was saying to Gavin before we started that we want to focus on doing and not showing, and we've done a lot of work in the background. We're very lucky to have Cargill as a launch partner and a technology sponsor for us, and the first vessels will be theirs, and we're looking to get the first wing on a vessel by the end of this year, and very shortly we'll be also announcing a technology partner who will help deliver the technology to our clients going forwards. So where we are at the moment, WindWings are they're now fully quoted in the constituent parts through various vendors around the world. As I mentioned, we have a global maritime partner who's been liaising in that procurement process and will be overseeing the assembly, installations at the shipyards, and then dealing with warranty, maintenance, crew training, and support throughout the life of the product. We identify that we're a relatively small engineering house, and we need a global partner to deliver to the global shipping companies. And I guess my closing comment to everyone is that we can't see the wind. It's invisible, of course, but as a group, as an industry, we've got to do a better job of measuring and recognizing the performance that wind can bring. And fuel reduction versus EEDI is a perfect example of that. You know, I think the published data for a rotor is 8-9%, and its EEDI values are only 3% saving. And likewise on ours, if we're looking at 30% saving, we're still only looking at an EEDI increase of 10 or 12%. So there's some work to be done as an industry to ensure that that as a whole, wind power is recognised for the benefit and the huge potential that it actually has.
Thank you very much,
Gavin.
Simon. Thank you very much. Very, very interesting. I can see the Spinnaker Tower there as well. So,
and our office.
Oh, very nice. Okay, so I'm gonna go on to just a second. Let me go on to side by side.
Was that all right?
Yeah, no, that's great. That's great. So I've got a few discussion points there, and I think we could probably sit here all day discussing all of the aspects of the.
Shall I stop sharing? There we go.
Yeah, there you go. I think we could probably speak all day on every single slide there.
Sure. It's always hard to compress it.
It's a fascinating. It's a fascinating area, and I have the challenge as well of condensing everything that you're doing down into a few slides. But I really appreciate that. I mean, the things that I was getting from that presentation is that you've really adopted a holistic approach to this. Multi-stakeholder, takes a little bit longer to get these things into the market. And I was just wondering, your DNA is coming from the sort of racing yacht design. What were the specific challenges of kind of taking that into a commercial shipping?
I think the challenges are mainly perception. The perception is that you design a race boat, how can you possibly engineer something that's got to be robust enough to go through the sea, and you don't know how badly tankers get treated, and actually it's an engineering challenge and you're optimizing to an objective. Now, if your low cases and your objectives are higher, you're still only as good as your weakest link, and by good, thorough engineering, and it's the same if you're designing a race boat to a very low reserve factor, or a wing to a higher reserve factor, or a bigger robustness factor. You've got to engineer thoroughly, and you're only as good as your weakest link. And actually, I think that the drive and DNA and the in-depth kind of attitude that we bring from the race side actually benefits an awful lot, because it means, yes, we might take a bit longer, but we dive into the details in more detail. And because we're used to engineering to low reserves, we know that whatever reserves we set, we're going to achieve.
Yeah, it seems, I mean, what you were saying in one of the slides was that pretty much there were no sacred cows. You weren't coming in with very preconceived ideas, that you were kind of challenging everything, putting everything on the table.
Yeah, as I said, actually, before we tried to design a wing, we designed the tool to analyze the performance of the ship as a whole holistically. Because if you don't understand and you can't model accurately in a digital twin and a simulation world how something's going to behave, you can't optimize and find out what the best solution is. Because something, and I see it all the time when you look at this, something might look really good on the surface, but it has a knock-on effect on lots of other things on the ship. And then the result, for example, if you have a lot of side force, you have a lot of leeway. A lot of leeway induces a lot of drag. That drag can create a yaw imbalance, and then you need more rudder angle. Your monk moment can end up off the front of the vessel, which means you have dynamic directional stability. And unless you're taking less dynamic directional stability, unless you're taking all those factors into account and taking a view of the ship as a whole, and you're designing in isolation in a silo, you're only kidding yourself. And the only way you're going to get found out is when you put it on a ship. And you know that if you put it on a ship and it doesn't perform as you predicted, that's the end of your product. Yeah. So we want to do a good job. We want to make sure we've simulated accurately our performance using, what are world-leading tools. If you can simulate the performance of a foiling America's Cup boat within 0.1 of a knot, we can use the same techniques to simulate the performance of a ship, maybe not to 0.1 of a knot, but to a very high resolution. And then we can say confidently, in these conditions, this average weather data, this route, this ship, this is what you are going to save. And we can, put on, back that up with science, if you like.
And my question, on some of your slides, you were focusing on bulkers and tankers there of quite a large size. Yes. Is there an optimum size that you've been looking at, particularly that is how can I say, is the most beneficial or the best segment for this technology? Not really. It's about practicality, and
the bigger vessels you can fit more wings and bigger wings, and obviously the smaller vessels you can fit smaller wings or less wings effectively, or a combination of both. Obviously tankers are a little bit easier in terms of deck space. The bulkers are more of a challenge, and we've got another concept that's not there. It's the same wing, but the way it folds is differently. That allows good access still for loading, because obviously loading in port of a bulker is a critical part of its operational profile. That's easier on the larger vessels. Some of the handy bulkers where you've got cranes and things in a way, that starts to become more of a challenge, because not only you've got to stay out of the way of the hatches, you've got to avoid the cranes as well.
Absolutely.
So that's assuming you want to take the wings down. The wings are designed so they can remain up in any condition. They feather into a very low drag configuration, which is a big advantage of a wing. Actually, when it's not operating, its drag's very low. And through simulation and simulators that we've developed, we've actually been able to prove that it has what effect it has on the maneuverability and turning circles of ships, for example, and show that that's very, very minimal. And
you talked about sustainability. And it's a word that we all bandy around. Sustainability in the sense of, I think you made a comment, very, very clear comment, that yes, we want to save carbon, we want to have all the environmental benefits of wind. So it's an abundant energy source out there, uniquely accessible to shipping, but it's got to be economically viable.
Absolutely.
Now, can you just unpack that a little bit more for us?
Yeah, shipping is still a business, right? And there's still a threshold of what people are going to pay for shipping things around the world. And what we can't do is come up with some fandango solution which saves an awful lot of CO2 emissions and reduces greenhouse gas emissions if effectively the end customer is not going to be able to pay for it. So a big part of what we do is looking at the business case, ensuring economically it works. And I truly believe that this technology is going to be supplementary to other technologies that are going to help. As I said, there's no golden bullet. You're not going to save. We're not going to get to the emission savings we need to get to with just wind, or just it's going to take a combination of things. And I'm sure future fuels are going to play a big part in that. But of course, future fuels or carbon taxes are going to be expensive. So if we can reduce the amount of fuel we are consuming, if we can make vessel hulls more more efficient, which is another area we're working, is looking at how a hull for a sailing ship would look. If we can combine those all together and we're reducing fuel consumption, even if it's a carbon neutral fuel, it now makes that carbon neutral fuel more viable economically because you've got to burn less of it.
Yeah, no, and I think we're seeing that it's highly likely that for the first 5 to 10 years, those fuels will be at a premium as well. Yes. And maybe not available everywhere around the world at the levels that we need them.
And then, of course, in terms of CapEx and OpEx for the wing, when we've been developing that, that's been at the forefront of our mind, ensuring that we are using construction techniques which are not only well known to the shipping industry, and we extensively use steels, for example, traditional shipbuilding methods, because they're cheap, they're reliable, they're well known, but also then using composites where it's adding significant performance. So it's a blend of cost versus performance, and always looking at that return on your business case.
Yeah, and I think I've seen this in a lot of the projects. It's a trade. You as you say, you can go for the bells and whistles on everything that does everything, and nobody can afford it. So
but what we've tried to do is geometrically come up with a shape that's forgiving, that is not too dependent on the finite tolerance on the build. This is not an America's Cup wing. This is an industrial wing. And part of our optimization and simulation process is ensuring that it's forgiving for either slightly out of tolerance build or through life degradation. The surface will degrade. It's obviously going to have certain service periods through its life, but you don't want the performance to fall off a cliff. And you've got two options when you're optimizing something. You can optimize something which has got a very peaky performance profile, and you can get right to the top of that peak, and you can save the ultimate amount, but you don't stay there for very long. Or you can do something which is a bit flatter, got a bit more of a plateau. You give away a tiny bit at the top, but in the real world, when you get on the water, your net savings are going to be higher.
Yeah, no, absolutely. That makes a lot of sense. Just a final point. I wanted to expand just a little bit on, and you touched on this to a degree, on the sort of support mechanisms around wind. Things like weather routing, the forecasting that we have now, new materials, automation, digitalization, all of these kind of support mechanisms that are around. It always makes me think, 5-6 years ago, really, these weren't in shipping. They were there, or they were very, very young in shipping. Now we see a lot of this stuff is coming through into the shipping world. Is that making it easier for us, or how could I say, lowering the barriers to bringing that wind propulsion in?
Yeah, I mean, it's fundamental technology that has to work together. And actually, when you look at weather routing, the weather routing algorithms you need for a wind-assisted ship are different to a traditional weather routing algorithms that are currently used. And we are developing and delivering a full product suite. So we'll deliver with the wing an on-ship version of ShipSeat, which will give the option for weather routing, specifically for using our wings, with the ability to have variable speed and variable routing, and incorporate the full holistic ship model. So we're looking at optimizing propeller pitch, for example, on a variable pitch propeller boat, but looking at optimizing engine RPM, rudder angle, the way the wings are trimmed, and giving that either in an advisory way or directly integrated into the control system of the ship. And then the wings themselves, their trim will be automatically automated in its control through the ship seat package. Right.
That makes a lot of sense, and I think we're seeing it across various different technologies. The building blocks are being put in place now. We're not talking about even 5 years ago, let alone 20 years ago. when we first saw, or we saw a sort of resurgence in interest in wind propulsion.
We can't be having sailors on the boat, right?
Yeah. Well, yeah. Somebody put it as how important is it for training, and it, to a degree, yeah, there is some training. It helps to understand what's going on, but pretty much you want a one button push.
Exactly.
And you're observing, you're maintaining that system.
Yeah. And that's exactly what we're delivering.
Now, okay, so that's all fascinating, and I've got about another 20 things I wanted to discuss with you, but I think we're going to move on to the quick fire stuff now. So these are a series of questions. We've got about 5 minutes left in the run, and I'm just going to fire these off. You can give a yes or no answer, but a single sentence answer would be great. So I'm going to get personal first of all. How did you get into sailing?
I grew up sailing from as young as I can remember. My father was a classic wooden boat builder. When I was literally in a cot, I was on a boat in my front garden my dad was building. Apparently, I knew the actions of tools before I could speak. So I think I was destined to be in this industry.
So you're living the dream.
Yeah, exactly.
Brilliant. Okay. What in the development of this particular sail or system, what's been the most significant challenge that you and the team have faced, and how, and the follow-up question to that is, and how did you overcome it?
Yeah, I mean, I think the most technically challenging part is that simulation tool set we've talked so much about. We're really lucky that we've got years and years of development from the America's Cup to draw on, and knowledge and experience. But ships are really complex things, and everything has an effect on everything else. And to accurately simulate in a reliable, repeatable, and flexible way, and flexibility is really important because we need to be able to swap in and out components and see what effect it has. What if we want to put the wings on a different ship that has a significantly smaller rudder? What does that do to performance? And I can tell you, it has a big effect. So, building that tool set was cornerstone to the project.
That was a little bit of a job interview sort of question, wasn't it? So you got the job anyway. Okay, you did touch on this before, but do you think retrofits or new builds are going to be the most active for wind propulsion technologies in general?
I think they're both going to be equally as active. As I touched on, we're going to have we're planning to retrofit by the end of this year, and followed up by a new build run, and they've both got pluses and minuses, I think. And I think I don't think there'll be a differentiation. I think both of them are going to be highly active areas if we get this right.
Okay, great. And I've got two more quick ones, and I'm asking this one to everybody and putting them on the spot here. Have you calculated your carbon footprint for the solution?
We have.
You have. Excellent.
We have. So we have a tool set that was actually developed through the whole of the last cup cycle. So a carbon footprint tool, which is actually available to the whole industry. It's publicly available, got published at the end of the last cup. So we use that to develop our footprint. Obviously,
that's excellent.
We're still looking at logistics, where we're going to build, transport, tooling, and obviously tooling is actually a considerable part if you look at the carbon footprint or something like that. So there is some how many wings are you going to amortize that tooling over in terms of its carbon footprint. Sure. But yeah, it's obviously an important part of the big picture.
And you've got the wider sort of environmental footprint and circular economy issues as well.
Exactly. And let's not hide from the fact that we have some pretty large composite elements. That technology for recycling is not there yet. There is a lot of work going on in that area. The wind turbine industry, especially the offshore wind turbine industry, it's got a much bigger problem than we do right now. And it's going to be solved, and I think it will be well solved by the time we get to the end of the life cycle of these products.
Yeah, no, I agree. I agree. And please do send me the link to the carbon footprint tool. I'll pass that on. Final one. Again, this is a little bit of the job interview question again. If you could change one thing about your approach to bringing this to market, what would it be? Over the last 2 to 3 years, something you got to the end of the process, you really wish we'd spend a bit more time or invested a little bit more effort in X. What would that be?
We're obviously not at the end yet, so it's hard to say.
Fair
but,
enough.
You know, I think the quicker we can do it, the better. You know, we're running at this as hard as we can, but making sure we have the right partners in play. We've been really, really lucky with Cargill. They're a great supporter of the technology. And, you know, as I said, we'll be announcing very shortly our marine industrial partner, if you like. But, you know, I probably wish I found those earlier, to be honest, because they've been a great help.
That would always be nice, wouldn't it? And I think, you know, just talking on that timing, something that we've discussed within the association quite extensively is the time is right now. A lot of the big shipping companies are the decisions that they're making for their 2025, 2027, 2030 movement. They're making those decisions now or lining up technologies that they're going to be. So I think it's a good timing.
Yeah, it feels like the stars are aligning, doesn't it?
Absolutely, yeah, and more work for me, more work and a few more grey hairs for me. But anyway, that's all part of the job. Simon, I'm going to give you just a sort of 1 minute, 1 to 2 minute sort of round up opportunity. So if you'd like to give the audience a bit of a takeaway, hand it over to you.
I think my takeaway on wind energy in general on shipping is it can be a major part of the future. It's not a simple thing to simulate. It's not as straightforward as some might think, and you do have to look at it holistically. It's not going to be the be-all and end-all to solving the problems of the world when it comes to greenhouse gas emissions in the shipping industry, but it can be a significant contributor to those reductions. And if we design ships going forward synthetically with technology as a whole in mind, so not just wind technology, but how all new emerging technologies kind of integrate and work best together, I'm sure we can get over the hump.
And I would completely agree with that. I think that integrated, holistic approach is absolutely the way forward. So, Simon, thank you very much for joining us today and sharing your thoughts on this. And as I said before, I think to be continued. We'll do a part 2 in the not too distant future.
Definitely.
Thank you. So, and I'd like to say thank you to all of the audience. We will have another Listening to the Wind interview next week. And if you have any questions, I know that either Simon or myself, Simon obviously on the BAR Technology Solutions, myself on the wider wind propulsion technology issues, but also, please reach out to Simon as well on those. More than happy to answer those. So thank you very much for joining us, and fair winds to all.
Thank you.